Hello, ladies and gentlemen, boys and girls. We are at the end of our 2010 Euclid Math Contest. We are at question number 10, and that's going to be it. We just have this question to go. Now, usually the last question is particularly challenging. However, in more recent years, they often describe a situation, and then they sort of give you one question where you just have to sort of understand what they mean, and it's usually a very simple computation. So I always try and encourage people, at least do 10A. It's usually two very simple marks to get. But let's dive into the question. For each positive integer n, let t of n be the number of triangles with integer side lengths, positive area, so they can't technically be a degenerate triangle where the sides are sort of on top of each other, and perimeter n. Okay, so integer sides and things like that. So, for example, t of 6 is 1, since there's only one triangle, an equilateral triangle, with sides adding up to 6 there. Okay, with 2, 2, and 2, they say. Alright, so we're trying to count the number of triangles with a given perimeter. Now, I seem to recall, and this is a long time ago, but a friend of mine managed to find an actual formula. I think Tn has a formula. I think it involves a couple floor functions and some weird large numbers and things like that. I get the feeling that 6, you have to do the floor function when you divide by 6 or something like that. I just remember in about grade 9, this is well over a decade ago, somebody mentioned Ralph had got a formula to calculate this sort of stuff. I don't know if we're going to actually need to create our own formula for that, but that was well before this question was created. So this isn't a new concept. We're just having to sort of do that in this question. So in A here, we have to figure out T10, T11, T12. And in doing those computations, I think we're going to sort of learn to streamline the calculation process. Maybe we'll learn how to calculate some TNs, maybe not others. So, for example, they give us 3 of them. I'm thinking maybe remainder when it comes to multiples of 3 and that sort of a thing might be useful. Just before we do A, just to give us a little bit of guidance, let's look at B and C as well. If m is a positive integer with m greater than or equal to 3, prove that t of 2m is the same as t of 2m minus 3. So maybe there's at least a little recursion. If you've got an even number, you can take 3 away and you can still get the same number of triangles. That's what this is saying. Okay. So that's something to consider. And C part, determine the smallest positive integer n such that t of n is greater than 2010. This makes me think I might want a formula, or certainly some rough approximation process. How to apply B? Well, just off the top of my head, if we want the smallest, I know it can't be even because there'd be a smaller even one. So that might at least narrow it down, and then maybe I just need to learn how to do t of odd numbers. Just things to think about as we start the question off. Now let's get into it with A. We want T10, T11, and T12. But thinking about later parts of the question, it might be a good idea to understand triangles. And really, when it comes to the side length, the only thing you can say is that by the sort of the triangle inequality, which is to say the sum of the other two sides has to be greater than if you pick a side, the sum of the other two sides is bigger than that, is what I'm trying to say. I'm also trying to write at the same time, and I should never do that. Now, usually this doesn't matter, except with the biggest side. So on my picture, I've got C. They don't tell us. We don't care about specific orders, do we? No. So we could say something like. Now, I have to allow for equilateral triangles, so we'll say less than or equal. We'll just say C is always the biggest, A is always the smallest. This will be a useful thing. So in order to... And I guess if they have to be positive integer side lengths, we'll have to... not greater than 0. Not greater than or equal to 0. Greater than or equal to 1. Because they will have to be positive integer sides. So in order to form a triangle, we just need... So these guys here are called the triangle inequalities. just need to satisfy C is less than A plus B. Because B being less than or equal to C automatically makes this one true, and A being less than or equal to B automatically makes this one true, because the other numbers that you're adding are guaranteed to be positive. Okay, so C has to be less than A plus B. Can this narrow some things down for us? Can we learn a bit more, or do I just need to start plugging in numbers? Well, having one inequality with C makes me think maybe I should take a look at other inequalities with C. So, for example, I know that if n is the perimeter, then this turns into C must be less than A plus B plus C is equal to n. So this tells me that C must be less than n minus C, and I guess that turns into 2C is less than n. I suppose we could also say C is less than a half n. I wrote C there. So that's a nice, useful inequality. That'll narrow down the C's that I have to pick. And if I narrow down C, well, that limits the possible values for A and B. Can we also maybe get a minimum value for C? Because obviously C can't be as low as 1 and things like that. There's sort of a bare minimum we need to have. What else could we have? Well, n is A plus B plus C, but A is less than or equal to B is less than or equal to C, so I guess this is technically less than or equal to 3C. And then we get a little something like this. So C has to be greater than or equal to, so summarizing, what do we got? C has to be greater than or equal to 1/3 of the perimeter, and has to be less than, strictly less than, 1/2 the perimeter, also called the semi-perimeter. So this narrows down things a little bit. I think we can do sort of similar work. Once you pick a value for C in this range, you can probably narrow down values for B and get an inequality there, and maybe then get an inequality for A in terms of B, which is ultimately in terms of C, and things like that. Things to think about for the future. Nothing's immediately coming to mind. I think maybe if we do a few cases now. So we want, what, T is 10, so N is 10. And so C has to be, it's a less than sign. So C is between 4 and 5. So C's got to be equal to 4, so that's pretty nice. So what does that tell me? A plus B has got to be equal to 6. B has to be less than or equal to 4. So I guess we could have AB is 2 and 4, or it could be 3 and 3. So A is less than or equal to B, which is equal to 6 minus A. I'm just trying to do the same work I did above, so I guess 2A is less than or equal to 6. So yeah, A is at most 3, and yeah, there you go. You can't do 1 and 5, because then B would be the biggest. So what does that tell me? T10 equals 2. There's 2 possibilities. You can get a 2-4-4 triangle, or you can get a 3-3-4 triangle. That's it. Okay, so that's T10. 2 cases there. Now I am a little interested in T11 just because it's odd, and by my observation between B and C, I think if we're going to attempt C, we should be paying attention to the odd ones. So n is going to be equal to 11, so that means 11 over 3 is less than or equal to C is less than 11 over 2. So 4 less than or equal to C, and this time we can get less than or equal to 5, because 11 over 2 is 5.5. So we've got cases. C could be 5, And then A and B are 6. And so A is less than or equal to 6 minus A again. So in general, just a little observation, A is less than or equal to N minus C. These are the possibilities, and I know A is always greater than or equal to 1, although we saw with 10, you can't actually get 1, so there might be a bit more to that. But this is I think, a useful... Oh, sorry, 2A. So this minus A. So 2A is always less than or equal to N minus C. So I think that's a useful observation. No matter what our choice of C is. It's gonna... And I might be able to get a better expression for that later as well. But it's good to know. So in this case, 2A is less than or equal to 6. So A is 1, 2, or 3. I'd really like to get a lower bound for A, if I could. But we can get AB is... We'd have 1 and 5, so I guess you can get 1 this time. 2, 4, or 3, 3. So that's 3 possibilities there. What if C was 4? Well, then 2A would be less than or equal to 7. That's going to give us even more possibilities. Let's just stop for a moment. Can I think of another a way to limit A even more? Not necessarily sure I can, but what would we have? 4, 4, 3 is really the only option, I think, for this one. But I'm just trying to think ahead. And when you're doing the Euclid, depending on whether or not you feel like you can get B or C, you might not care to be doing this think ahead stuff. But I'm committed to doing question 10 because I always do question 10. So I'm just trying to think ahead and trying to save myself time by making observations now. And nothing's immediately coming to me, so B has to be less than or equal to 4. And, oh, well, there's something. A plus B has to be greater than or equal to... It has to be greater than C, so that's a useful piece of information. I don't know how that can help me right now. Okay, so that's true for B. B is also equal to 6 minus A, and it's got to be greater than or equal to A. Well, So we know A is less than or equal to B, but A is going to be 7 minus B. And so B has to be greater than or equal to 2 times 7. So that gives me a range of values for B here. So let's make an observation about that. So first of all, that's going to mean B has to be equal to 4, so 3, 4 is the only pair AB. So T of 11 is going to be 4. We get 4 triangles, 1, 2, 3, 4. But this is an interesting observation. So once C is chosen, A plus B has to be equal to N minus C. A has to be less than or equal to B. So N minus C minus B is less than or equal to B. So N minus C is less than or equal to 2B. So we've learned that N minus C over 2 is less than or equal to B is less than or equal to C. The next thing to think about is, is it possible that all b's in this range will work? Because if that's the case, I can get a nice formula in terms of c for the different b values, and then once a c is chosen, I can tell you how many without actually having to work them out like I did over on this page. Will that always work? Well, can b always be as big as c? That's sort of the question. If that's the case, so if you can get one that works for the n minus c over 2, which should work, the question is, can b be as big as c? So if b is equal to c, then a plus b plus c is equal to a plus 2c, which needs to equal to n. Well, c is definitely less than n over 2, so 2c is definitely less than n, so n minus 2c, which is equal to a, is definitely greater than 0, and that will work. So what can we say? If I know the c value, I can tell you how many b values will give you a triangle, and that would give me a nice quick way to count. So we'll come back to this, but I think this is important. Now it depends on whether or not this is an integer or not will affect our count for b values. So we might have to worry about if n is even and c is even, and parity issues are something we'll worry about later. But let's see if we can finish a and then move on. So T12. So what can we have? We have 4 is less than or equal to c, less than 6. So c equals 4 or 5. But now we can go through things a little faster. If c is 5, then 12 minus 5 over 2 is less than or equal to b is less than or equal to 5. Let's write out our range here. 12 minus 5 is 7, divided by 2 is 3.5, so b is between 4 and 5, and each of those will work, so b equals 4. Your a, b, c, I guess I'll write them all together now, is going to be 3, 4, 5, and if b is equal to 5, we get a triangle of 2, 5, 5. So there's 2 from that. And if c is equal to 2, then 12 minus 4 over 2 less than or equal to b less than or equal to 4. Well, that would be 8 over 2. B is going to have to just be 4. And that gives me 4, 4, 4 as the sides of my triangle. So T12 is going to be equal to 3. So T10 was 2, T11 was 4, and T12 was 3. And we've finished A. You would have done it a lot faster if you weren't, like I am, on the hunt for interesting little properties that can help us work through the problem. Okay. So, good work. We got the values. I'm confident those are the values, and I'm also confident we've got an interesting sort of idea brewing in the back of our head to count Tn. Now, we have to know things like the parity of n, and the parity of the c values, but I think something's coming together, and we might actually be able to get a formula for Tn. Okay. So B part, if m is positive integer with m greater than or equal to 3, prove that T2m is equal to T 3m minus 1. Or, sorry, 2m minus 3. I don't know why I said 3m minus 1. 2m minus 3. Okay. So, I mean, it seems to me, if you got 2m, couldn't you just, I mean, the minus 3 is sort of screaming out, just shorten each side by length 1. That won't change any of the inequality, will they? So we might say something like, suppose ABC gives a triangle with A plus B plus C equal to 2M. I think, it just seems natural, shorten each side by 1. But we have to be careful, must A necessarily be bigger than 1 over here, because we'd need A minus 1 to be bigger than 1. And would the inequality still hold? So we'll say, at least this is what I'm going to start with. So we claim A minus 1, B minus 1, C minus 1 gives a triangle of perimeter 2M minus 3. So it's clear that the values add up. That's what made this so attractive. But now I'm starting to doubt things. Just because C is shortened by 1, but A and B are shortened by 2, and it's possible that the inequality screws up a little bit. So we need to check A needs to be bigger than 2. And we need, so we know C is less than A plus B. And so C minus 1 is less than A minus 1 plus B, but can I really do that minus 1 again? I'm nervous about that. Maybe this isn't the right way to go about it. Well, we also know C is strictly less than 2M over 2, which is equal to M, because that's an inequality we've worked out, we've noted, we've written down. And as you go through this and you find important inequalities, I would suggest as you're writing it up, put like a box around it so you can refer back to it later and say things like observation 1, observation 2. Especially because I've already worked my observations in while I was computing things in the midst of part A. So I'm definitely not going to win any points for organization. But putting boxes around and saying, you know, this result, we're applying that here, is a good thing to note. Just as you're doing this. So C is less than M. I can guarantee that. So C minus 1 is less than M minus 1. But I don't know if that's small enough for this. So A plus B, which is going to be 2M minus C, has to be bigger than 2M minus M, which is equal to M. So A plus B is bigger than M. So C less than M less than A plus B. So C minus 1 less than M minus 1 less than A plus B minus 1. And since we've got an inequality here, that implies that M minus 1, if you subtract another 1, since they're all integers, the worst you could do is actually equal. But that's okay. So combining these two facts here, C minus 1 would still be less than M minus 1, which is at least A minus 1 plus B minus 1. Okay, the triangle inequality did work out. So there's the triangle inequality. There's the right perimeter. And now I just need to make sure A is as small as possible. We haven't actually figured out how to get A in terms of things. But what can we say here? I know B is at most as big as C is. And that's definitely less than M. So B plus C is less than 2M. Well, actually, it's less than or equal to... Yeah. Let's stop using inequality or the strict inequalities. So B and C are both less than or equal to M minus 1. That means B plus C is less than or equal to 2M minus 2. So A, which is equal to 2M minus B minus C, is at least 2. So A minus 1 is greater than or equal to 1. And so are the other sides. So triangle inequality is satisfied. They're all positive side lengths. And the perimeter adds up. So yes. If this is a triangle for T of 2M, then A minus 1, B minus 1, C minus 1 is a triangle for T of 2M minus 3. So, what have we shown? Every triangle for T2M is also a triangle for T2M minus 3. So, I guess we've shown this. Now we have to go in reverse. So now suppose ABC is a triangle for 2M minus 3. I suppose we could change the letters to D, E, F, just to make it a little easier to read, but I'm going to stick with ABC, just because all my inequalities are written like that. So, I claim you can reverse it. The reversing should be a little easier to show. So I claim this gives a triangle for perimeter of 2M. So we check the perimeter. 2M is indeed A plus 1 plus B plus 1 plus C plus 1 because it's A plus B plus C plus 3. And that's 2M minus 3 plus 3. Okay, so the perimeter is good. The triangle inequality holds. So we know A plus B is greater than C. So add 2 to both sides. Yeah, this is definitely the easy direction. I probably should have started with this. So triangle inequality holds. And finally, 1 is less than or equal to A. So that means that 1 is less than or equal to A plus 1. So all sides are positive. And there we go. Okay, that's really what we need to do. To make a triangle of a non-degenerate triangle, we have to satisfy the triangle inequality. They specifically, in the question, say integer sides. Integer side length, so it's got to be positive. Positive area means triangle inequality, perimeter n, so we've got each of these three things. Oops, that's not one. Each of these three things has been satisfied, so we do get the right amount of triangles. So what does that tell me? That every triangle for 2m minus 3 is also a triangle for 2m, so we get this inequality, and combining the two, we get the answer to B, which was the T2m and T2m minus 3 are the same thing. Okay. Now C part, we want the smallest so that T of n is the year. T of n is greater than the year. Okay. Maybe we couldn't actually get the year. Fine. Okay. So for C part, first note that the smallest such n must be odd. If n equals 2k, that is even, and t of 2k is greater than 2010, then t of 2k minus 3 is also equal to this value and greater than 2010 by b, and this here is an odd number. So, okay, we're looking for odd numbers, and that might narrow down the search, I guess. What else might we need to know? Well, if we had a formula, maybe we can get a formula for odds, because remember I was talking about parity. So just a couple notes or observations. So the first one, n over 3 less than or equal to c less than n over 2. That's a useful one. And for a given c, for each b in the range, it was n minus c over 2 less than or equal to b less than or equal to c, n minus c minus b, b, c is, I guess we could say, valid triangle. Right? That should work. Yeah. I suppose we might want to just re-justify that a little bit. What could we say here? Okay. So first of all, so c being less than n over 2 means that b plus c is less than n over 2 plus n over 2, which is n. So a, which is n minus b minus c, is greater than or equal to 1. Good to go. Now, the biggest a can be needs to be, the biggest a needs to be smaller than the smallest b. So that means this part is good. We get a triangle there, and we already know b has to be less than or equal to c. If b is actually equal to n minus c over 2, then a is equal to c minus n minus c over 2. Oh no, it's n minus. A is equal to n minus c minus n minus c over 2, which is equal to just n minus c over 2. So a is less than or equal to b. Okay, I'm satisfied that these two conditions hold. So this means together, this means for a given c, we can count number of triangles having a perimeter of c, or sorry, perimeter of n and c as a length. Okay, and it would be, well, if c is, let's say, if n minus c is even, then this is actually an integer. And that would be, so how do we count an integers in a range when you have c minus n minus c over 2 plus 1? If n minus c is odd, then b is between these values here, you have to go up a little bit. Imagine it were 7. 7 over 2 is 3.5. Well, b can't actually be 3.5, so you go to the next biggest integer, which is 4. So n minus c, 7, plus 1, 8, divided by 2 gives us 4. And so that's how many triangles there. So you'd have c minus n minus c plus 1 over 2 plus 1 triangles. And we can simplify these in the next page. Now, we are only considering an odd. So what this really means is if c is even, we get so c odd. We'll do c odd first. Then n minus c is even. So number of triangles is going to be c minus n minus c over 2 plus 1. C even means n minus c is odd. So number of triangles is c minus n minus c plus 1 over 2 plus 1. Right? Those were the formulas we just had. Yep. Okay, good. So, based on the c values, we're all set. Now, we can rearrange a little bit of this. So, c minus, so we get 3c over 2 here, minus n over 2 plus 1, and we can bring the over 2 in as n minus 2 over 2. And here again, the minus turns it into 3c over 2 minus n plus 1 over 2. Bring in the plus 1, but it cancels out with the minus, so it'll be minus n minus 1 over 2. Okay. So these are simpler formulas to work with. So c's will alternate even and odd because we have a range of values. We have a range. It can be as low as n over 3. It can't be bigger than n over 2. It'd be really nice to know in this range the evens and odds, I guess, because let's say, suppose in this range C takes on E even values and O odd values. Then number of triangles, it'll be, both formulas had 3 halves C. So it'll be 3 halves times the sum of possible C's, which is something I can work out. And then it'll be minus, so if C takes on an even value, it'll be minus E times n minus 1 over 2. And if it takes on an odd value, it'll be O n minus 2 over 2, right? Okay, so I just need to know the range of C values, how many evens and how many odds are in that range, and then I can figure out Tn. Okay, so what can we do? I have to worry about whether or not this is an integer or not. And I have to worry, actually, I don't just have to worry about whether or not they're integers, I also have to worry about whether or not they're even, because maybe this one, maybe there's an even number, or an odd number of values C can take on, but we start with an odd number. And if there's an odd number, you'll start with an odd number, you'll end with an odd number, and that'll be more odd numbers than even numbers. So I need to worry about divisibility by 2 for this. I need to worry about divisibility by 3 for this. And And then I need to worry about divisibility by 2 again for both endpoints. So, do I really have to work out 12 different cases? So, consider the remainder of an odd n when divided by 12. Do I really need 12? Would 6 not suffice? So, no, because if n is just even, like if I knew n was even, we called him 2k, then I'd just know it was k at the end here, and I wouldn't know, well, if k is odd or even. So, yeah, I guess I need that extra factor of 2, darn it. Okay, so we could have n be 12k plus 1. So we're going to get 6 different cases based on the remainders here. So there's n. We'll get even and odd here. We'll say range of c values. That is to say, so we'll start with 4k, dividing that by 3. The remainder when you divide that by... Wait, no. I have to be very careful here. When I divide this by 3, I'll get 4k plus a third. So I'd start at 4k plus 1 here. And at most, I could be up to, since all of these are odd, n over 2, I'll just subtract 1, and so we'd go up to 6k. So the number of c's, and then, yeah, the number of c's here will be, I need more space. So range of c's, number of c's. And then if I start with, okay. So 4k plus 1 less than or equal to c less than or equal to 6k. Let's just get the ranges and then we'll work out the number of possible c values. Here, divide by 3 will actually work out, so 4k plus 1 is still your starting point. And now it's 6k plus 1 is your ending point. Divide by 3 here. We have to round up because you get 4k plus 1 and 2/3. That would round up to 4k plus 2 for your lowest actual c value. Dividing by 2, 6k plus 2. 6k plus 3 here. The endpoints are really easy to work out. Last one, 6k plus 5. Okay, dividing this by 3, you'll get 4k. Then you'd get 2 and 1/3, which has to be rounded up to 3. Dividing this by 3, you get 4k plus 3, nice and simple. And then 12k plus 11, 4k plus, that has to round up to 4. Okay. Divide it by, and then you round up. Okay. So 1, 1, 2, 3, 3, 4. Okay. So the number of k values I can get is 2k c values. Every number alternates even and odd, so it'll just be k's here. So not a big deal. This, we've got 2k plus 1 different c values, because again, how do you figure out how many numbers are in a range? You take the biggest number, subtract off the smallest number, and you add 1 just to make sure you haven't double counted. Here we're going to get a difference of 2k. Here's, 2k plus 1, my mistake. Here's another 2k plus 1. This will be 2k plus 2. That's another even one, so we can immediately put that over here. Finally, we'll get 2k minus 1, so this is also a 2k plus 2 situation. Okay, now, there's an even number, there's an odd number up here. We'll either have one more even or one more odd. Now, we definitely start with an odd number. So, we'll have, we definitely start with an odd number, so we'll have one more odd than we have even. Here, we definitely start with an even number, so one more even than odd. And we start with an odd number, so one more odd than even. Okay. I'm not entirely convinced I couldn't have done that without... Maybe I didn't need so many cases. I thought the ends here were going to make a bit more of an important play, but I guess not. Although, if I didn't have that, I'd just have k many c's and I wouldn't know if it was even or not. Okay, maybe I did need 12. I'll worry about that later. I've got a chart that works, so we're just going to move on. Never, ever stop and worry about the efficiency of how you're doing your question while you're doing the question. Unless, you really think you're wasting a ton of time and there might be a better way to do it. But this is working. This is maybe double the amount of work I might have needed to make the chart, but it's working. Okay. So for each of these, I now know E and O, and we can talk about sum of possible values for C. Now, we roughly start and end at the same amount, so we can... Using the 12k plus 1 case, we can at least get a rough idea of how T odd grows. Okay. I think in theory we should be able to show that the T's increase for the odd numbers, but let's just get an idea of what numbers we might be looking at. So we'll compute one case. So how do we find the sum of the C values? Well, we know where they start and where they end. And how do we find the number of numbers in the sum of the numbers in a particular range? Well, you figure out the sum of the numbers up to 6k. You subtract off the sum of the numbers up to 4k plus 1. The numbers before that. So we'll get 6k times 6k plus 1 all over 2 minus 4k minus 1. Oh no, 4k plus 1. All over 2. So where we start and just before where we start and where we end. And then we have E, which in both cases here it's going to be k. And then it's, sorry I'm bouncing back and forth, n minus 1 over 2. So n minus 1 over 2 will be 6k. And then it was n minus 2 over 2, right? Yeah, and then we'll have 12k minus 1 over 2. Okay. So there's a formula. There's a formula. Now I want things like this to roughly be bigger than 2010. So roughly this is 3/4 36k squared minus 16k squared minus 6k squared minus, again, roughly 6k squared. That'll be 20. 20 divided by 4 is 5 times 3 is 15k squared minus 12k squared. So 3k squared, and the other numbers are going to be similar because it's all a bunch of 6k's and 4k's and k's here. So about 3k squared. So using this idea, If I want t 12k plus an odd number, well, we'll say a. No, we've already used a, haven't we? That's one of our side lengths. Although I'm not really talking about triangles much anymore. I don't know, p. So if I want that to be greater than 2010, roughly I need 3k squared to be greater than 2010. So we can bust out the calculator now, divide it by 3. So 670, square root that. It's going to be about 25. So I might start thinking about numbers 12 times 25, so 300. So 301, 303, 305, 307, and so on like that. It was, I think, 25.8. I'm just going to redo the calculation because I've already forgotten. 25.8, so maybe on the higher spectrum, maybe close to k equals 26. So that would be, 313 and things like that. So I'm going to guess n is, 25 would be 3. So 25.8, let's actually, if k were 25.8, multiply that by 12, so about 310-ish. But those are the numbers I'm expecting to get there. I got 309.6, but I didn't use all the decimals here. So, well, I guess we can compute some of these. 309 sounds like a reasonable place to start. 309, you might want to say 311 just to be on the safe side. Now, it's worth it to know that this was an absolute rough approximation. I might be massively overkilling, in which case then we're going to have to figure out how to jump around. But yeah, this part here is roughly 13k squared. Roughly. So 309, I mean, it's as good a place as any, 309.6. So 309 is 12 times 25 plus 9. So we are in the 5th case there. 12k plus 9. So, okay. T of 12k plus 9. 3 halves. I'm going to have to keep bouncing back and forth. 6k plus 4 is our end point. 4k plus 3 is our start point. So we want just before that, so the sum of the first 4k plus 2 numbers. Minus, what's E? Oh, they're both k plus 1, so that's nice. And in this case, it'll be 25 plus 1, 26. And now it's n minus 1 over 2, so that would be 12k plus 8 over 2, so that would be 6k plus 4. And then minus, and now it's minus 2, so 12k plus 7 over 2. So with k equal to 25, this gets me 6k is, so we have 154 times 155. Minus 102 times 103. Divide that by 4, multiply it by 3. I get 10,023. And then minus 26 times 154 again. 4,004. And then 26 times 12k is going to be 300, so 307 divided by 2. So that's minus 3991. So 10,023 minus 4,004 minus 3991. And I get 2028, and that is bigger than 2010. Great. It's actually pretty close, too. Is that the smallest one? Well, we could check the next smallest, 2007. We could check the next smallest after that and things like that. We don't know that the terms necessarily increase. There's nothing in our approximation, and even if I wrote out all these formulas, I doubt I could actually prove it, to say that things are necessarily increasing. We already saw with T10 that it's 2, but then T11 was 4, so this thing doesn't necessarily grow in a strictly upward fashion, but maybe the odd numbers do. Well, I guess we could check T307, because that's also nearby, and if that's smaller than... Or should we try and show that it's increasing? Because I'm pretty sure it should be increasing, because if you just add more to the perimeter, all you could do is possibly have more triangles. But let's check T307. Let's just keep checking until we get something that's less than 2010, because then we will at least have an idea. So that would be 12k plus 7. K is again 25. So that's going to be 3 halves, 6k plus 3, 6k plus 4, all over 2, minus, so what would we start here? If we divided by 3, we'd get 3k plus 3, or 4k plus 3, so we'd be starting at 4k plus 2 again, 4k plus 3, all over 2. I just want to go back and really quick and double check I got the right starting and ending points. Good. Minus, we started an even number, so evens will be bigger, and we'll have 2k plus 1 of them, right? 2k plus 1, we'll have k evens, k plus 1 odds, and the odds go with the n minus 2 thing. So k evens, k plus 1 odds, because we started an odd number. I looked at this number first, but no, we start at the second number there. And that's n minus 2, so that's 12k plus 5 over 2, and this is just 12k minus 1, or 12k plus 7 minus 1, so 12k plus 6, divided by 2, 6k plus 3. Yes. Okay. Oh, this number and this number will always match. Yeah, cool. Okay, so now with k is 25, we have 3 halves. Well, let me just grab my calculator and start plugging things in. So 6k plus 3, that's 153 times 154. Subtract 102 times 103. Divide that by 4. Multiply that by 3. We have much smaller numbers now. 9792. Well, that's not... Yeah, it's actually... that is pretty small. Seems odd. I'm just going to double check. 153 times 154 minus 102 times 103 divided by 4 multiplied by 3. Okay, yeah, it's fine with me. Minus 25 times 153, so 3825, minus 26 times 305 divided by 2. So that'll be 3965. So 9792 minus 3825 minus 3965. And we get 2002, which is less than 2010. So N309 309 is the smallest, assuming T for odds is never decreasing. So that's the last thing I would need to show. But other than that, 309 is the right answer. And that's actually kind of nice that we managed to, just with that 25.8 thing, sort of hit it right on the head. So, finally, lastly, we show. It's been quite, it hasn't really been a dull moment, but it's been quite the adventure with this one. Lastly, we show that t 2k plus 1 is less than or equal to, because maybe adding in 2 to the perimeter isn't enough to necessarily give you an extra side. But this would be enough. So, we just need to show, well, what could we do? If ABC is a triangle with A plus B plus C equal to 2K plus 1, C less than or equal to, less than A plus B plus C, or less than A plus B. So it satisfies the triangle inequality, and 1 less than or equal to A, less than or equal to B, less than or equal to C. I don't just want to increase C by 2, because that might cause problems with the triangle inequality, so I guess we should split it over. Don't want to add 1 to A, because that might make it bigger than B. I guess B and C. So then observe A, B plus 1, C plus 1 has A plus B plus 1 plus C plus 1 equal to 2K plus 3. 1 is less than or equal to A is less than or equal to B plus 1 less than or equal to C plus 1. In fact, this one here can become a strict inequality, but we don't need that. And finally, C less than A less than B, less than A plus B implies that C plus 1 less than A plus B plus 1. Just add 1 to both sides. Therefore, we get a triangle for the count in TK plus 3, T of 2K plus 3, and that's enough. That's enough to show. We don't need to show that every triangle in T2K plus 3 comes from one of these. We just need to show that each one of the 2K plus 1 perimeter triangles can be extended to create a different one in 2K plus 3. So the numbers are necessarily equal, and that, at long last, finishes everything off. It has been quite a question, and frankly, quite a contest. Some very, very interesting questions. 9 was a bit of a pain. 10 I feel like it could have gone worse, but it seemed kind of long. I definitely feel that we really lucked out there with that 309, because, what did I say? I said, you know, with K around 25, you could have had 300. Already that was a rough estimate, incidentally. But you could have had from 300 to maybe if K was 26, so that would have been, what, 323? So that would have been a whole range of values. So the fact that I used that decimal and got 309, that was nice, but it certainly could have taken a lot longer, I feel. I wonder if there was a different approach where the 309 was a bit more obvious. Because other than that rough estimate of 3K squared, I don't think... Well, anyways. I might look up their solutions and see if they had something a bit more straightforward. I also am going to experiment a little bit, but on my own, just to see if that 12 was necessary. Maybe I could have gotten away with just using 6. Not that it turned out to be too much of a problem, but that's more because I found 309 so quickly. Yeah. All right. So that's the 2010 Euclid. That's it for all the 2010 papers. I guess 2011s will be rolling out whenever I get the chance and things like that. So if you're interested in writing Euclids, you can look up more Euclids that I'll be going through. And if you're going to write the Euclid this year, I wish you very good luck on that. Feel free to like or subscribe or leave a comment if you had a different way of doing this or any of the questions. I always like hearing these sorts of things. But other than that, you guys have been wonderful, and take care. I'll see you in a future video.